We want to look at a particular Laplace inverse. We want to look at this one where it says, suppose you see something like e to the minus cs f of s. What does that become? And according to our table, they write it as uc of t f of t minus c. Okay, so what the heck does that mean? Well, so suppose I ended up with something where I wanted to take the inverse Laplace transform of like e to the minus 3s, and I had something like 1 over s minus 5. Okay, what is that? Well, what we do is we take the 1 over s minus 5 and we say, well, the Laplace inverse of 1 over s minus 5, well, we look that up, and that's e to the 5t. Okay, so we've got that Laplace inverse. And so what that means is if I want the Laplace inverse of this whole thing, then that is equal to, well, the uc, so that's u3 of t, and we'll refresh that, what heck we're saying there in a minute. And then we have this f of t minus c, so we have e to the 5 t minus 3. And so that's our Laplace inverse, is we forget about that part for a moment. We just do the Laplace inverse of this other part, and then in the t, we substitute in the t minus 3. Now actually this is very consistent because, what is u3 of t? Well, it's another way to write it is the unit step function of t minus 3. So what this means is everything's been shifted to the right by 3. So we used to have, if we think of e to the 5t, let me go down just a little bit more. Okay, so here's our graph of e to the 5t. Looks like that. But then what we did was, everything started at t equals 0. Well, now what we're saying is we're going to go out here to 3 and start that same sort of thing. We're going to do that. And we're going to do our e to the 5t at that point. Except, well, if I want that curve here to exactly match what I'm seeing there, just shift to the right, well, we know that we have to do a t minus 3 like that. And so that's what the combination of this and that are telling us, is that we've just taken this curve that we start, that we think of here, e to the 5t, we've shifted it 3 to the right, and started there, but we have 0 before that. Nothing happened before that. Then all of a sudden we wanted to work with this e to the 5 t minus 3 function at that point. And we don't have to write it that way. We could write it as like e to the minus 15 times e to the 5t. I mean, actually, we could write it like that, but typically you'd probably see it like that to really point out that we're thinking of the shift. Okay? Now, so why is that true? I mean, why is this our rule? Okay, well, let's take a look at that. We'll start a new page. And so let's take that unit step function, or I'm going to rewrite it as an h for Heaviside, just to kind of remind us that that's another way to talk about this is the Heaviside function. f of t minus t0. So we have that. And now suppose we want the Laplace transform of all of that. Well, then that's equal to the integral from 0 to infinity of e to the minus st times that heaviside function t minus t0 f of t minus t0 dt. Now, since that's the heaviside function or unit step function, it's 0 until we get to t0, and so I can rewrite this as the integral from t0 to infinity of e to the minus st. But remember, once it hits t0, that function is just 1. And so I'm just going to drop it out of there as far as the symbology, because it's just 1. And so that's f of t minus t0 dt. Okay, so that's what we have. Now, I don't know how to finish that other than I'm going to do a substitution. I'm going to let tau equal t minus t0. So you see that's I'm doing a substitution in there for the f. And well, so integration by substitution, I need d tau, but that's just dt because t0 is a constant. And now to help me out in some other ways, I'm going to have to substitute for t itself. While solving for t itself, I have t equals tau plus t0. Okay, so I have that. And so now if I substitute those things in, well, we have the integral. Now t0, that was t equal t0, so t0 minus t0 is 0, so this starts at 0. When t goes to infinity, so does tau, so we have that. Then e to the minus s, and t is tau plus t0. And then we have our substitution here, f of tau and d tau. Well, multiply through by the minus s up here, and we'll get e to the minus s times t0. Those are constants. t0 is a constant. As far as this integration is concerned, s is a constant. And so we're going to have e to the minus s t0 like that, times the integral 0 to infinity e to the minus s tau f of tau d tau. Oh, but hey, that's just the Laplace transform of f. So this is e to the minus s t0 Laplace transform of f. And I'll put it back at t now. Like that. Or we can write it as e to the minus s t0 f of s. Okay, so that's where our formula comes from. So there's the formula they mentioned in the textbook, that if this is what you have in your Laplace space, so you've done the transform, you do this, and you recognize that you have that thing, and then times a bunch of other stuff that hopefully you can take the inverse Laplace transform of, then what you do is we come back here, and if you recognize that sort of thing like we have here, you simply worry about taking that Laplace transform of the 1 over s minus 5, okay, like we did, and then substitute in, since that's a 3, we substitute in our t minus 3 in for t. So we did that, and then just toss that unit step function or heaviside function that changes at 3 in front of it. Okay, so that's the idea So if we, if we run into, well, I'll put it down here, so if we run into anything where we want to take that Laplace inverse of e to the minus ct, and then we have something else, times all this other stuff involving an s, well then we try to find the inverse Laplace transform of that little f, but then we do the unit step function or Heaviside function. So we get the Heaviside function of t minus c, and then our f at t minus c. Okay, so we just figure out what f of t is, and then do that substitution. Okay, and so that's the idea. Again, another quick example might be suppose I have e to the minus 2s times 5 over s squared plus 25. Well, then, hopefully I could figure out with Sage or looking at a table or, doing some work that 5 over s squared plus 25 fits the sine of 5t inverse Laplace transform when we go that direction. And so what that would mean is my answer here, if I take the inverse Laplace transform of this thing, that is simply, now I'll switch back to the unit step function. That's u of t minus 5, and then sine of 5, t minus 2, sorry, t minus 2, and 5 t minus 2. Okay, is what we get for that inverse Laplace transform. And there's no reason why that 2 couldn't have matched here. It's possible that those could all relate to the same number, but again, they're in different places. This is our C, and this 5 was in the place of A over s squared plus a squared, the Laplace transform of sine of AT. Okay, so there you go. That is the inverse Laplace transform when we see this particular sort of form. Okay, that's the way we handle it.